Thank you for the invitation. I'm very happy to be here. So I will talk today about a work in progress. It's a joint work with Daniel Greb, Tim Kirschner, and Martin Schwald. So both Tim and Martin are here, so if you wish to talk with them after the lecture about the project, please feel free to do so. So we are working with complex K3 surfaces, so I will start by recalling a few basic things about K3 surfaces and then explain the motivation for our project. Okay, so recall that a complex K3 surface is a compact, connected, complex manifold of dimension 2 such that the canonical bundle, so let's say I'm calling this K3 surface X, the canonical bundle of X is trivial and irregularity 0. Okay, so maybe the most basic example of a K3 surface is the Fermat quartic. So the Fermat quartic, so that is defined as the set of points in CP3. So Z0, Z1, Z2, Z3 in homogeneous coordinates, such that these points satisfy the following homogeneous equation. So Z0 to the power of 4 plus Z1 to the power of 4 plus Z2 to the power of 4 plus Z3 to the power of 4 is equal to 0. All right, so I'm going to think of a K3 surface as the following quadruple. So that would be X, E, omega E, and G. So by X I will denote the underlying differentiable manifold, by E the complex structure, by omega E Kähler class, and by G the unique metric associated to omega E with holonomy SU2. So I'm going to recall this a little bit now. So by X we denote the underlying differentiable manifold. By a theorem of Kodaira, as differentiable manifolds, all the K3 surfaces are the same. So if you wish, you can think as for X as the underlying differentiable manifold as the Fermat quartic. Okay, by E, I denote the complex structure. And now by a theorem of Siu, every complex K3 surface is in fact a Kähler manifold. So that means that you have a Kähler metric H on the holomorphic tangent bundle of X, and the second cohomology of the K3, which is the cohomology of interest for a K3 because K3 surfaces are simply connected, has a Hodge decomposition. So H2XC is the direct sum of the 2-0 part, the 1-1 part, and the 0-2 part. And the Hodge numbers, so the dimension of these three pieces are 1, 20, and 1. And in particular, associated to the Kähler metric, you have G, a Riemannian metric. And you have omega, a Kähler form, which on vector fields is related to the Riemannian metric by omega E v w is g of I v w for v and w vector fields, and omega E is a real closed 1-1 form. So in particular, it will define a cohomology class in the RAM cohomology, and this class, the Kähler class, I will denote by omega E. So this is an element of H11 intersection H2 XR. And the last well-known result that I need, which basically realizes a K3 surface as the minimal dimensional example of both a Calabi-Yau manifold and a hyperkähler manifold. It's a theorem that's a consequence of Yau solution to the Calabi conjecture. So this says that each Kähler class omega E determines a unique metric G with holonomy SU2. Unique metric G with holonomy SU2. So in particular, this says, maybe I write this here. This says that we have complex structures, let's say J, K, complex structures on X, such that K is equal to the composition of I and J, and minus J composed with I, and such that the metric G is in fact Kähler with respect to an entire sphere of complex structures. So such that G is Kähler with respect to any complex structure in this set, which is defined as T1I plus T2J plus T3K, where the Ti's are real numbers which sum up to 1. Yeah, so this set is, of course, isomorphic to S2, which is isomorphic to CP1. Sorry?
Ti squared.
Yes, thank you. Yes. Okay, so so in fact, so if you put together all these complex K3 surfaces that you get by letting the complex structure vary in this sphere, you get a family. So all these K3 surfaces fit into a family, and that's the Twistor family. I will just recall this very quickly in a picture. So the Twistor family will sit over P1. So here down I have CP1, and I think of a point in P1 as a complex structure, and the fiber, so in the total space, so let's say I call this Z, as a differentiable manifold, this will just be the product of X with P1. So this is as a differentiable manifold, but as a complex manifold, this will not be the trivial product. So the fiber here, this fiber can be identified with it will be isomorphic with X with a complex structure IT if I sit over a point IT in CP1. So if I just take a point in the fiber, so that will be an element of the K3 surfaces and the complex structure IT, then I can define the tangent space of Z at this base point just as the direct sum of the tangent space of X at the base point X with the tangent space of P1 at the base point IT. Now, of course, P1 comes with a natural complex structure, so I'm going to denote this here by, yeah, let's say J naught. So then I can define a complex structure on each tangent space of Z at this point, just by taking the direct sum of the complex structure on X. So that's just IT. And the complex structure on the tangent space of P1, so that would be J naught in the tangent space at IT. Yeah, and the theorem is that the complex structure so defined fits together into an integrable complex structure on Z. So Z is then so Z is then a complex manifold with this complex structure. And Z with this complex structure is called the Twistor space. So this is Twistor space. And this projection map, so this is just projection to the second factor, this becomes holomorphic. Okay, so there are a few other interesting properties of the Twistor family that, in fact, completely characterizes the Twistor family, and I will come back to this later on. Okay. So now, if I look at the second cohomology of my K3 with integer coefficients, I have a natural intersection pairing on this. And it is well known that this pair has the structure of an even unimodular lattice of signature 319. And by result of Mirner, any such two lattices are isomorphic, so I can choose an isomorphism to a fixed lattice. So I will start first by fixing L, an even unimodular lattice of signature 319. So in particular, this L is a Freezy module of rank 22. And let's say L, so I will just put it here, also comes equipped with a non-degenerate symmetric bilinear form. So we have a non-degenerate symmetric bilinear form on L. So I can choose an isomorphism from my second cohomology to the fixed lattice, which respects the intersection pairing. So I'm going to call this by phi, denote this with phi, and any such phi is called a marking on my K3, and the pair X, and while together with the complex structure that I started with, and phi, it's called a marked K3. Okay, so now I will restrict for a little bit to the fixed lattice that I chose, and denote first by LR the real vector space that you obtain by extending scalars, and by LC the complex vector space that you obtain by extending the scalars, and the bilinear form that you obtain just by extending the scalars over C. I'm going to denote it by B. So this is B, but of course I will keep in mind that B is in fact defined over R. And then I have a natural complex conjugation on LC with fixed point set LR, and I have a Hermitian form. So I have H on LC defined by H of xy is B of x y bar. All right. Now I will fix a basis of LC. So that will be V1, V2, V3, V4, and so on, V22, which is orthonormal with respect to the Hermitian form H. So orthonormal with respect to H, such that each element in this basis is real in the sense that it's invariant under the complex conjugation. So I have that Vi is equal to Vi bar. So in particular, this also says that this this basis is also an orthonormal basis with respect to the bilinear form B. And then I will take the following decomposition of LC. So these guys are the positive vectors with respect to H. I'm going to denote their span by L plus. And the last guys are the negative vectors with respect to H, so that will be L minus. And I have an orthogonal decomposition of LC with respect to H as L plus direct sum L minus. Okay. Let's see. Okay, so now I will use this basis and the lattice that I fixed to define the period domain. So I start first with the following quadratic. So I define Q to be the set of lines in PLC such that for all the points x on this line, B of xx is equal to 0. So these are just isotropic lines with respect to B. And because B is non-degenerate, Q is smooth of dimension 20. And now I would like to identify Q with the flag manifold. And the way to do this is as follows. You take G, the automorphism group of the complex vector space LC, which preserves the bilinear form B and which has determinant 1. Then, you can check that G acts transitively on Q. So you can identify Q with G mod P, where P is the isotropy at the chosen base point, but in fact, you can also check that P is a parabolic subgroup of G, and that identifies Q as a flag manifold, as a G flag manifold. And in the basis that I chose, I'm going to denote G with SO22C. All right, so that's about Q, and inside Q we define now the period domain associated to the lattice that I fixed. So that will be D is now the set of isotropic lines in Q, such that for all points lying on this line, which are not 0, that will imply that H of xx is bigger than 0. So these are positive lines with respect to the Hermitian form H. Yeah, in the same way as we did it here, you can also identify D with what's called the flag domain. So, but maybe I should just mention before that D is open. So this is an open condition, so D is open in Q. So it's a complex manifold, but it is not algebraic. And if I denote by G naught, the automorphism group of LC, this time preserving the Hermitian form H and of determinant 1, then this is a subgroup of the complex group G, and it is in fact a real form of G. So this is in fact a real form of G, and then one can also check as an exercise maybe that G naught acts transitively on D. So you can identify D with the quotient G naught, let's just say P naught, some isotropy. So this realizes D as a G naught flag domain inside my flag manifold Q. So this is a flag domain. So that is, if you let the real group act on the flag manifold Q, then you will have open orbits, and any such open orbit is called the flag domain. So D is one such flag domain inside Q. And in the basis that I chose, G naught, I'm going to denote G naught with SO 319. Okay, now how this relates to K3 surfaces. So maybe I just write here that D is called the period domain associated to the fixed lattice L. So I want to consider now the moduli space of marked K3 surfaces that I denote by MK3. So this is moduli space of marked K3s. Now this space exists. It's locally a complex manifold of dimension 20. So locally complex manifold of dimension 20. And there is a very explicit construction for this involving pairs of period points and Kähler chambers, so I will not go over that. But the problem is that this space is not Hausdorff. So this is, it's not Hausdorff. You do have, however, a period map, so global period map from the moduli space to the period domain. So I have P from MK3 to D. So this just sends a marked K3 to the image under the marking of the H20 part in the Hoche decomposition. So that is, of course, that is a one-dimensional line. So it will, of course, end up in a line. So it will end up in PLC. But one can also check that this line is isotropic with respect to B and positive with respect to H. Okay, so this is the period map. And what's known about this? So everything. So it's holomorphic, it's surjective, and the local Torelli theorem says that it's a local isomorphism. It is, however, not injective because of the non-Hausdorffness of the moduli space. But of course, having a marking, is an additional structure. So you would like to get rid of the structure. So you want to consider the moduli space of unmarked K3 surfaces. So getting rid of the structure means modding out by the following, by the action of the following group. So I will denote by gamma the automorphism group of of the lattice, preserving the bilinear form. This, of course, acts on the marking. So if you compose the marking with an automorphism group of the lattice, you will get another marking. But this is also naturally a subgroup of the real group G0, so it will also act on D. And you do get a period map on the quotients, so you'll have MK3 mod gamma to D mod gamma. Now this map is now injective. However, the problem that you get here is that gamma does not act properly discontinuously on the right-hand side, on D. So gamma does not act properly discontinuously on D. So unfortunately, you get a very bad quotient. So D mod gamma is not Hausdorff. Okay, so in practice, it's of course very difficult to work with this map. However, associated to D, so to the period domain, there is another natural space. It's a complex manifold on which gamma acts properly discontinuously. And that was the motivation for our project, was to look closer to this space and see what we can say about this space in terms of the geometry of K3 surfaces. So I'm going to first define this space for you and then explain a little bit about our project. Okay. All right, so to define this, we go back to the period domain. So I will first define this space and then recall again how this relates. Okay, so I define by C0 the intersection of PL plus with a quadratic Q. So recall that this L plus was just the space in LC that's mapped by the first three positive vectors with respect to H. And this basis was also orthonormal with respect to B, so the restriction of the bilinear form to L plus is also non-degenerate. So in particular, I'm going to get C0 is a degree 2 curve in PL plus, which is of course isomorphic to P2. And that implies that my C0 is isomorphic to P1. And so this is a curve, this is a degree 2 curve in D, and I'm going to call this a base cycle. Okay, now as we did before, so we saw that the period domain and this algebraic manifold where it sits can be defined group theoretically. We can in fact do the same about this curve. So if I denote by K0 the stabilizer in G0 of the decomposition of LC as the direct sum L plus L minus. And by K, the same thing, but now I take the stabilizer in the complex group G of this decomposition. Okay, so remember that this decomposition is just the orthogonal decomposition given by the Hermitian form. Okay, then one can show two things. So that K naught is a subgroup of G naught, but in fact K naught is a maximal compact subgroup of G naught. So K naught is a maximal compact. And furthermore, K is the complexification of K naught. And C naught, so my base cycle is both an orbit of the maximal compact subgroup K naught and of the complex group K. So I will explain this in a second in a picture. So this is K naught. Let's say I choose a base point L naught. So maybe I draw the picture here. Okay, so what's the situation that we have here? The situation is like this. So we have this Q, this smooth quadric of dimension 20 in PLC, and we saw that this Q is, that this Q can be identified with a flag manifold. So that is G mod P. Then inside Q, we have an open orbit of the real group. This is a complex manifold, and this is the period domain associated to the fixed lattice that we started with. And now I look inside the period domain, and I consider this degree 2 curve. Let's say I draw it like this. So this is C naught. And then I observe that I can also define this C naught group theoretically using a maximal compact subgroup of G naught. So what happens is that I consider a maximal compact subgroup of G naught, and I let it act on D. And this curve that I obtained is in fact the unique orbit of this group, which is a closed complex manifold in D. But what I can also do, I can take its complexification, K, and I can let this complex group act on the bigger thing, on Q, and then this orbit is also the same as the minimal dimensional orbit of the complex group acting on the bigger thing. So it's both an orbit of the small group and of the complex group. All right, so now I will use this curve to define the space of cycles associated to the period domain. And these are defined as follows. So first, as a set, I define MQ, which you can think of it as a subset just as a subset in the Chow variety. So I will consider the set of cycles which are obtained by moving this base curve that I started with the complex group G. So C is obtained by moving the base curve that I started with an element of the complex group G. So I start moving this curve with G. Of course, because I move with the complex group, I will go out of D. And then it can happen that I intersect D, but it can happen that I completely go out of D. All right. So this is, of course, just by definition, it follows that G is also a smooth curve of degree 2. And MQ can be given the structure of a complex manifold. So MQ is a complex manifold. And this can be done as follows. So the easiest way to do this is as follows. So I start with the curve in MQ. So this is obtained by moving C naught with the element G. Now I use the definition of C naught. This was just PL plus intersecting my quadratic Q. Now this is of course the same as moving first the tree plane with G and then taking P of that and intersecting it with the quadratic. So it's P of GL plus intersecting Q, and G is an element of the automorphism group of the bilinear form B. So the restriction of the bilinear form B to this new three-vector space is also non-degenerate. So yeah, so B restricted to GL plus is non-degenerate. And yeah, in fact, you can show just using basic linear algebra that the group G acts transitively on the set of three-dimensional vector subspaces of LC on which the restriction of B is non-degenerate. So that will identify MQ now with a G homogeneous space, G mod, and what's the isotropy in G of this L plus, where we said at the beginning it's K. So that's G mod K. So this is an affine symmetric space, affine complex symmetric space. And I look at this G mod K as embedded in this Grassmannian of three planes in LC. So elements of this are basically elements of this Grassmannian on which the restriction of B is non-degenerate. Yeah, okay, so maybe I just write this here quickly. So I will think sometimes of this curve just as PV intersection Q, where V is now an element of G mod K. All right. Now, of course, you want to move this curve, but you would like to stay inside D. So we want to define a space of cycles associated to the period domain. So that is, I'm defining now MD. So I start, so I take the set of cycles inside MQ such that this stays inside D. Okay, so I move with a complex group, and I take everything that stays inside D.
May I just ask, those conics which you describe here, they are the Twistor curves, is that right?
Sorry?
These conics which you describe here, they are related to the
Yes, yes. So I will explain that in a second, how they are related to the Twistor family, yes. Yeah, okay, so because C naught is compact, you can show that MD is open in MQ. So now I can also, yeah, so now MD is also gets a complex structure just simply from as an open set in MQ. So in particular, one thing that I will need later on, the dimension of this space, MD, is just the dimension of G mod K, and that's 3 times 19. Okay, so now of course there are other natural cycle spaces associated to D, so the Barlet cycle space or the Douadi cycle space. So you can ask yourself, how does this group theoretically defined cycle space fit into that story? And so when you compare MD with the Barlet cycle space, you can show that the Barlet cycle space is smooth at this base cycle that we started with. So you can consider an irreducible component in this Barlet cycle space, or the irreducible component that contains this base cycle. And a priori, this irreducible component will be much bigger than MD, because MD only contains smooth degree 2 curves. So in this irreducible component, you could have something like this, or you could have double lines. So you will also have singular curves. But in fact, you can show that MD is equal to an irreducible component in the Barley cycle space. So maybe I just denote this with C, C1. So this is an irreducible component in the Barley cycle space of 1 cycles in D. Okay, so what's the picture now? And this is now the motivation for our project. So I have here, what do I have? So I have this bigger cycle space MQ, which we said is G mod K, so it's an affine complex symmetric space. Now inside this thing, so if I go back to this picture, I said I'm moving this base cycle with a complex group, but I can first start with moving the base cycle with the real group. Then I will for sure stay inside D. And if I move it with the real group, and I take the isotropy of this orbit, so this is just G naught modulo K naught. So this is a real symmetric space, and I'm going to explain this later on, but I mean this is the part that's related to the Twistor family. But this MD is somehow bigger than this G naught modulo K naught. So you can think of this as being real cycles obtained by just moving this cycle with the real group. So now you can consider the following problem. So you can let G naught act on G mod K. Now you see that on this orbit, G naught acts properly because K naught is compact. So you can ask yourself, what is the maximal domain inside the G mod K on which the action of G naught is proper and which contains this real orbit G naught modulo K naught. And this is now a theorem of Alan Huckleberry. And the theorem says that MD is the maximal domain in G mod K, which contains the real symmetric space, which contains the real symmetric space G naught modulo K naught, and on which the action of G naught is proper. Okay, so in particular, we see as a corollary of this theorem that gamma acts properly discontinuously on MD. So if I look at the quotient, then this is Hausdorff, and in fact it's a Stein space. Okay, so having now defined MD, I would like to relate this to K3 surfaces and to the Twistor family that I started with at the beginning of the lecture. So let me just state the goals of our project. And then state some of the results that we got until now. So maybe I just put two goals here. So goals. The first one is to find a moduli interpretation for points of the cycle space MD and of the quotient MD mod gamma. So these guys will correspond, I will explain in a second, to what we called either marked or unmarked, what we call quadratic families of K3s. And an example of such a quadratic family, we will see it's the Twistor family. So example is the Twistor family. And the Twistor family, we will see, it will be a family that sits over these real cycles. So of course that we knew from the beginning, so our goal was to understand families that sit over the other cycles. Yeah, and then the second goal is to concretely understand the action of gamma on MD. So of course that means understand what happens if you go to the boundary where the action fails to be proper, and relate this on the K3 size with our family. So that will be the generations of these quadratic families. All right. So now, let me quickly clean the blackboard. And before I state the result, I want to recall just one more basic result from the theory of K3 surfaces. All right, so for me, at least for this lecture, I have a family of K3 surfaces. It will be a triple X BF. Now I'm going to call with X the total space, but don't get confused. So I have X and B are complex manifolds. F from X to B is proper holomorphic submersion. And the fibers of this family, I'm denoting them with XT, are K3 surfaces. So these are K3s with the complex structure induced from X. Yeah, okay, also for the lecture of today, at least I assume that B is simply connected. And if I choose a base point in B, I'm going to regard the family as a family of deformations of a central fiber, which I'm going to denote with X0. Then by Ehresmann, it follows that this family is differentiably trivial. So X is diffeomorphic to the product of the central fiber and the base. And if I have, so I have here my family, I have here the central fiber, and I have some other fiber. So ACT, and these are diffeomorphic. So such a diffeomorphism will induce an isomorphism in cohomology. From the cohomology of the fiber XT to the cohomology of the central fiber. So now, if I choose a marking for the central fiber, so an isomorphism to L, this will induce a marking on the fiber XT. So I have an induced marking. So basically I start with a marking on the central fiber, and then I will get a marking on all the other fibers. So I get a marked family, which I denote X, P, F, and phi. So this is a marked family of K trees. Alright, so maybe I also clean this part here. All right, and associated to such a marked family, I can define also a period map. So I will go from B to D. As before, for the global period map, I will send here T to phi of H20 of XT. Well, of course, just from the definition, so you see we get we have this inclusion given from the Hodge decomposition. So in H2 XTC, and what we have just said is that these guys all fit together into a trivial bundles, but in fact these guys also fit together into a holomorphic subbundle. So you have the following inclusion of holomorphic subbundles. So this is inclusion of holomorphic subbundles. So, okay, so now I have everything to state our first results. Okay, maybe I need one more thing. Sorry. So from the definition, I also need the universal property of the period map, and that is that the pullback of, so the period map is a holomorphic map to PLC. So then the pullback of O-1 from PLC is isomorphic to, of course, F lower style, so the push forward of the relative canonical. Oh, okay, then I state the theorem and then I'm done. Sorry. I had the feeling that I started a bit later, but I guess not that much later. Okay, so I will be very quick with the results. So the proposition. So first, what do we want to do first? First, we want to identify the families that lie over the cycles in our cycle space. So I say, let X be F and phi, be a marked family of K trees, and P its period map. Then the following are equivalent. So the first thing is that I have an element of G mod K inside these Grassmannians of 3 planes in LC, such that the period map is a biholomorphism between the base B and the cycle given by PV intersecting Q. And the second thing is that there exists a biholomorphic map from B to P1 such that the pullback of O minus 2 from P1 is isomorphic to, so F lower star, the push forward of the relative canonical. So for these reasons, I obviously call my families quadratic families. So now there's another, there's another property which will make it obvious that Twistor spaces are an example of these families, but I don't have time to give property C, so I will just give now one theorem. So, I say let's take Z, the total space of a quadratic family. So if you want, you can think of the total space of the Twistor family, so the Twistor space. Then I have the following things. So I have I have that the dimension, so the complex dimension of H0 of Z, TZ, so this is now sheaf of holomorphic vector fields on Z. This is 0. So this means that if I look at deformations of this family, the deformations are unobstructed. So deformations are unobstructed, and the universal family exists. And the second thing is that the dimension of H1 is, what do you think it is? It's 3 times 19. So that's the dimension of our cycle space. And I have some more things, but I will stop now because I'm already over time, I'm sorry.